All right, everybody. Hello. It is 8 a.m. here on the West Coast. We're gonna wait a couple minutes for everybody to kind of filter in and get on here, so you get to stare at me and my slide for a little bit in the meantime. But we do want to thank everybody for taking the time to come out here today. I do see a few people saying hi and good morning. We do appreciate it. I am stalking all the chats as we go. So, feel free to say hi or whatnot as we go. Good evening from Abu Dhabi. Congratulations on being at least the farthest chat away from me this morning or evening for you. Sorry. Gotta love time zones. 8 a.m. for me. So what is that? 6 p.m. for Abu Dhabi, something along those lines. And Brazil, thank you for coming out. I do appreciate it. 19 hours. Wow. Okay. Yeah, cheers to that. And from Poland, we very much appreciate that. PGA Tours here, so nice, sunny and steamy Florida for this summer morning, and Mexico, wonderful. And then, of course, we have the one guy from our company saying hi from Connecticut. Thanks, Joe. Appreciate that. But as you can see, we're trying to make this as interactive as possible. Again, we're just going to wait a few more minutes for everybody to filter in a little bit because not everybody is always on time. And if you know me, I'm very rarely the person on time. This just happens to be my show today. Milan, hello from California, Milan. We are very grateful that you are here. It's really cool. Just a little housekeeping as we go through and as we wait for a few other people to filter in. We want this to be interactive. It is just me today. It's me and my Stanley cup of water because I'll be talking for a while. So we want this to be as interactive as possible. So if you have any questions, feel free to put them in chat. Depending on how chatty everybody gets, I may not be able to keep up with it. So please don't be affronted or don't feel offended that I didn't quite get to a question in there. If there's a question that is left unanswered, we will get back to you on your questions. And as always, you can always reach out to myself or anybody else from TAG, and we'll be glad to answer the questions. Hopefully, somebody asks some questions that I don't know the answers to. Because one thing about HDR that's really interesting is to really understand HDR, you have to understand biology. You have to understand how the human eye works. You have to understand how computers compress video, how compression works, and so forth. There is very literally dozens of PhDs that are required for HDR to work and to really understand HDR. So this is intended to be high level, and I am definitely not a PhD. So if somebody asks a question I don't know, I'll be very happy if you don't, or if you ask a question that I don't know. But we will more than likely have to follow up at some point in the future. So I just kind of want to start that part off. So we'll give everybody about one more minute, and then we will kick it off. And then, of course, there is the person that always starts it off with the right and understand why no one can standardize on an HDR standard. That is correct. HDR, as we'll talk about it, because we're going to spend a little bit on the biology of HDR, it is tough on how to do a standardization of HDR sometimes. West Covina, California. That city got pretty famous about a decade ago from a TV show. And Mr. Ari Klingman from New York. Good to see you. Good, sir. All right. I'll tell you what. We've got about 30 seconds to go. I love the fact that we is from such a different part of the world. Sao Paulo, New York, Berlin. This is fantastic. So thank you all for being here. All right. We're going to get one more sip out of my sippy cup. And then in 5 minutes, we're going to start this off, which is right now. All right. Well, thank you, everybody, for being here today. We are very grateful that you've taken your time out to talk about HDR and to learn about HDR. Um, I've been saying this a little bit over the past couple of minutes, but for anybody that's a late joiner, we want this to be interactive. I am looking at the chat as we go through this. So if you have questions as we go through this, I will do my best to answer, depending on how many questions we get and how fast they come in. I may not be able to keep up with it and answer all of them. Hopefully, somebody stumps me with a bunch of questions I don't know the answers to. And we will get back to you on that. So you can reach out to myself or anybody from the TAG organization. We have people who are infinitely more knowledgeable in some parts of HDR than me. And so we are glad to bring those questions to them or myself and get back to you as soon as we possibly can. And yes, the nice thing about standards is there are so many of them. We're going to talk about that as we go through the webinar, why there is so many of them. So the first thing we want to talk about on HDR is color and dynamic range is an incredibly complex topic because it's not just a single standard, as a few people have properly made jokes about. It's a suite of standards, but also it's how does the human brain, how does the human eye perceive color? How does the human eye perceive light and contrast and differentiators between them? And there's a lot of tricks we do in the broadcast industry to trick that. So we are going to spend a lot of time on that. But this is the most important part. This is a very high level presentation. There is so many rabbit holes you can go down with HDR in terms of telemetry and with luminance and how the eye perceives it, or how does the math work when you do a LUT, or why do we do 12-bit instead of 10-bit and compared to 16-bit, and all these type of things. There's so many rabbit holes that go down that are amazing, but we have an hour. So the goal for this is to keep it high level. The goal for this is to just to talk about the basic terminology. What are what are the words? What are the abbreviations? And what are some of the bigger things that really factor into HDR productions today? There will be another webinar next month. And the webinar will have a guest from a broadcaster on with us. And it's going to be the applied version of today. So today is the theoretical. Today is the basis, the fundamental understandings of HDR. But there's going to be very little applied. How do we do this in television? How does this work today? How are people creating HDR today? There's very little of that in today's presentation. So that will be next month. So to tee it up next month, we will have another webinar, and that's going to be the applied methods of HDR. How does HDR actually work in the real world, in real world productions? And again, we will have a broadcaster from us. So let's first off, basics of terminology. HDR is not just HDR. HDR by itself is the reference to high dynamic range. Now, dynamic range implies light, contrast, brightness, luminance, that type of thing. But we in the broadcast industry kind of treat HDR as a catch-all because it's not just the dynamic range, but it's also we get more color. In other words, wide color gamut. So to start off on one of the fundamental terms, HDR is not just high dynamic range. HDR is also better colors, more colors, brighter colors, darker colors, so forth. So you get the dynamic range, but you also get what's called wide color gamut. So that's the first thing to start off on as the terminology. Now let's spend a little bit of time not on the broadcast or the engineering side at all. Let's talk about the human eye, because so much about HDR is about tricking the human brain and tricking the human eye. And if you look at the entire electromagnetic spectrum, the visible spectrum is actually a very small part. It's extremely narrow of what our eyeballs can see. And that's interesting because cameras can actually see a little bit more into the ultraviolet, and some can see into the infrared, but we kind of filter that data. We don't allow that data to happen. But the human eyeballs have a very narrow spectrum in which they can see. Here's obviously a much bigger picture of it, but you can see right there where what we perceive as colors is a very narrow portion of it. And one of the parts that really everybody needs to understand it, which is, for me, was an incredibly hard concept until I got it, which probably speaks to me a little bit, is there actually is no concept of color in visible light. It's actually the wavelengths of the RF spectrum that we receive. And the human eyeball is extremely narrow at the wavelengths that it can actually receive. But inside that very narrow band, you'll see from here, from the deep purples to the greens to the yellows to the blues to the reds, that the human eyeball converts photons to what our brain perceives as light by actually having pigment proteins that are sensitive at receiving short, medium, and long wavelengths. Now, granted, short, medium, long wavelengths is very relative to ourselves because it's still a very narrow band of light that we're looking at. But you'll start to see a bit of a trick that we do and a bit of a dynamic of the human eye that we use a lot in broadcast is you notice that the medium and long wavelengths tend to overlap a little bit, and they tend to overlap quite a bit in the green spectrum, at least as we perceive as the color green. And that's something that we use as a trick in the broadcast domain because the human eyeball is so much more sensitive. There is actually these two pigments that overlap at receiving RF light, or light in that exact spectrum. And it's key to point this out because this is an evolutionary step of humans. You know, if you go back, definitely not so much now, but you go back not just even a few thousand years, human eyes have developed an acuity for green, for foliage. You know, we want to be able to, if we're foraging for food, be able to find it. But also, if there's an animal hiding in the foliage somewhere, we're going to want to be able to see that foliage move around before it attacks us, right? So there's some evolutionary process on why the human eye has such a bias towards the green spectrum, at least again as we perceive it as green, and not so much in the reds and not so much of the blues. But we're here for an HDR discussion, right? Like, why does any of this matter? Why am I talking about how the human eye has evolved over the years to be sensitive towards green and not quite as sensitive towards blue and red? Why does this matter? Well, to be honest, we're all engineers. We want to make things as efficient as possible, and we only want to transmit the colors that we can see. You know, we can't see that well in infrared. We can't see that much in the UV, so filter it out and don't send it. But also, if you're having to compress video, why send a lot of data that the human eyeball can't see? So we're going to transmit the stuff we can see, and we're going to ignore the rest. And if you look through history of the broadcast industry, very narrow window in the overall evolutionary scheme that we're talking about here. But if you look at the broadcast limitations we've always had limitations up until just a few years ago with bandwidth. We never had unlimited bandwidth. You know, if we're talking about analog video, we had a pretty, well, broad by a lot of modern standards, 6 megahertz, but at the time it was extremely broad. But for actual video transmission, 6 megahertz isn't that much. So we had a pretty narrow envelope in which we can transmit audio and video. And then we went to digital with ATSC 1.0, which is fantastic. It got us into the digital domain, but we're still pretty limited on bandwidth, you know, 270 megabits, 1.5 gigabits per second. So we had to compress the video to be able to, both in analog domain and also in the digital domain, to be able to fit the video into the amount of bandwidth that we had. So as an industry, we had to make decisions on what can we drop out. But the reason HDR is prevalent now, and why does this matter, is these bandwidth issues that we used to have are long gone now for the past 5 or 10 years. I don't know about you all here at home. I would say I consider myself lucky. I've got 1 gigabit up and down for my symmetrical for my internet, so it's like $50 a month. It's fantastic. What we're finding is to get most good HDR content home, we need at least 4 to 5 megabit, which I think at this point is almost ubiquitous. So if anybody else, by the way, around the world has any kind of feedback on what kind of internet connections they have and what they're seeing as, at least in their countries, as prevalent for getting HDR content at home, feel free to drop it in the chat. Would always like to be able to look at it and feedback on it because, again, we want this to be interactive. But now this bandwidth for streaming television is becoming not an issue. We no longer have to compress a video that much. And actually, to be fairness, we don't really have to compress it at all, but at a certain point, it's just a waste sending a compressed video around. Also, we have the concept of ATSC3, which for terrestrial broadcast has removed a lot of those limitations because the way we're modulating the video, actually modulating the RF, and also encoding the video, we're able to get significantly higher amounts of bandwidth and higher quality video. So a lot of the limitations we're still running underneath are no longer there, but we still have to deal with it. So let's talk first about color, because this is the first step about HDR and where we came from and where we're going. This is a good kind of tee up slide. You'll see right here in the middle, we're going to go into a lot more discussion on this in the next few slides. But you see Rec 709, and Rec 709 is the very basics of how much color we transmit in the SDTV/digital domain. Analog is actually even a little bit less than that. But Rec 709 is what we have been doing forever. And all the rest of these other triangles you're seeing here, those are other video standards. So to the two gentlemen that made comments when we first signed on about how there is no common standard, yeah, you're right. I'm showing you at least 4 of them. As a reference, by the way, the larger color space you see here, the little rounded off one that goes all the way out, this is what the human eye can perceive. So remember that the human eye, how it perceives color is wildly different from human to human. Some people can see reds very well. Some people can't see reds hardly at all. Some people can see greens very well. Some people really can't. And so this is all very subjective to the person, which is the nature of HDR. HDR is so subjective, and we're going to see why, even in the standards as we go through. But just please realize that all of these little triangles we're going to see through here are all a smaller subset of colors than what the human eyeball can see. So there's 3 prevalent color options in the broadcast industry today. Rec 709, DCI P3s, everybody just kind of calls it P3, and then Rec 2020. So Rec 2020 is what the industry is doing HDR in today and wide color gamut. And this is when you're watching the amazing HDR 4K type videos, this is what it's in. Rec 2020 is fantastic because, as you'll see from on the right side of the slide here, it covers a very large amount of the visual spectrum of color. It is significantly wider than the Rec 709, and we'll go into a little more details about what is 444 and stuff shortly. But as a basics of terms, just know when you're starting to talk about HDR, true HDR production, they're going to be done in Rec 2020 or Rec 2100. So basics of terms, there you go. Also, you have DCI P3, which you'll notice here on this middle slide is a smaller section of color and luminance, especially compared to Rec 2020 and compared to that. DCI P3 is about 72.9%, 73% of Rec 2020 color space. They don't really care too much about resolution, supports 444, but here's the important part. Why is P3 even in this? Because it's covered by a lot of phones, Samsung phones, iPhones, iPads, Mac monitors, Google phones, things like that. They all support this P3 resolution. Interesting thing about Rec 2020, bouncing back to that real quickly, is as of yet, this will change, no TV or display can do full 2020 color space, which is interesting. Because if you do a production in Rec 2020, but no monitors can actually display 2020, how's it going to look to the end user? Subjective, right? And finally, we have Rec 709. And Rec 709 is what we've been doing since 1990. This is any digital broadcast we're doing today, anything that's SDTV or HDTV, or even a lot of the 1080p's that are not HDR, is Rec 709. And it is what it is. It's 8-bit, it's 10-bit. It is standard dynamic range. There is no extra colors. There is no extra brightness and luminance or anything involved in it. That's what it is, and that's what we've been doing. So when we talk about color space, again, these are the 3 that matter. Rec 709, P3, Rec 2020. In the future, almost everything we're going to be doing is going to be done in the Rec 2020 or Rec 2100 standard. All right, so now that we got colors done, let's talk about compression in a little bit. And get another drink from the Stanley here. Um, because we're engineers and because we've identified that the human eyeball is extremely good at perceiving green, and not so good at perceiving blue and red, we do we get ourselves some compression, and we've been doing this for a very long time on how we actually transmit green and red and blue. And we call this the YUV color space. And for me, this is always the hardest part to understand when I first got into broadcast is, why do you have RGB? Why do you have YUV and so forth? Reality is now that we have streaming and essentially unlimited bandwidth, there's no reason we can't start doing RGB productions, with the exception that no gear supports it. And it's a huge amount of bandwidth compared to what we're used to. So as long as we're using existing infrastructures, be it 2110 or be it SDI or whatnot, we're going to be stuck with some level of compression. And we use that as YUV. And what's interesting about YUV is Y, which is the green portion of it, is green covers your luminance values. It also happens to cover the green spectrum. U, which actually stands for the blue, is the difference between the blue and the green. And so you notice here, we're not showing all the luminance values on this blue projection part of it. We're just showing the difference in values between the blue and the green. And same with red. If you look at the V, the red projection, the amount of data we're showing for red is significantly less for the red of the blue than it is for the green. And so you're starting to see the fact that now we just found a way where we can send a lot of data for luminance, because the human eyeball in the green area is really sensitive, but the human eyeball is not very sensitive in blue, and it's not very sensitive in red. So we can send less data there, and then we can combine them to get a proper color image, or at least what the human eyeball perceives as a proper color image. And this is kind of a good little chart that talks about our subsampling. And this is to talk about the different, 444, 422, 420, and so forth. 444 is what we would all love to do. That means we're sampling red and green and blue in the same manner, with the same amount of data, with the same amount of bandwidth as each other. And what's fantastic about that is we don't throw any data away. It's great for post-production. Actually, it's perfect for post-production. And it's great for a lot of these workflows where you're going to archive content and go back to it later. The catch is because we're doing a lot more sampling and a lot more colors, it's a lot more bandwidth. And it's greater than 10-bit. It's actually 16-bit. So the amount of bandwidth per source flow goes up significantly. And at this point, really nothing in the broadcast live chain supports 444 in real time. Now, tons of file-based workflows are 444. If you shoot anything in the file-based domain, if you shoot anything for digital cinema, you're absolutely going to be doing RGB or 444. You would almost never be doing any kind of sampling or 420 or 422, because why would you capture less data than you need to? In the broadcast domain, we primarily now have standardized on 422. So 4 being the amount of sampling we're doing on green or luminance, and 2 is the amount of subsampling we're doing for reds and blues. 420 is what we've been doing quite a bit over 8-bit over the past couple of years. And then 411, I've actually never seen it in production. It exists. I've never used it in production. Every production I've ever done has been in 420 or 422. So that's the color sampling. And here's the interesting part. If you shoot a production in 422, or if you shoot anything in 422, but your production's in 420, who decides what data gets thrown out? How much red gets thrown out? How much blue gets thrown out? Or other way around, if you had a production that was done in 420, but your broadcast is in 422, you now have the availability to have more colors than you shot your production in. So how do you map that 420 into a 422 color space? Who decides what colors get added? Who decides what colors get removed? So everything about HDR and everything about wide color gamut is incredibly subjective, and we're going to talk about that quite a bit more. All right, now luminance considerations. This is talking about how bright the video is, what the contrast is, and so forth. Let's see. We do have a question that came in perhaps on foreshadowing, but camera captures. Are camera chips not really 444 chips downsampling? So, not to go too much down a camera rabbit hole, uh, if you have a 3-chip camera, those 3-chip cameras are actually doing 444, one chip dedicated to red, one chip dedicated to blue, one chip dedicated to green. If you have a single chip camera, they actually put filters on the front of every pixel of that single chip camera. And the ratio of green to red to blue filters on the front of that imager usually ends up becoming 422, or on some older cameras, 420. So you're getting into a bit of the camera physics there, which is a really, really fun rabbit hole to go down. But 3-chip cameras can do 444. Some digital cinema stuff that has very big imagers can do 444 off of that. But most broadcast cameras are actually designed to do 422 out of the camera head itself. Because again, for real-time stuff, 422 is good enough. Anybody doing digital cinema, anybody doing things for archiving, 444 is fantastic. All right, let's get to some more terms that we're going to throw around quite a bit. And by the way, thank you for that question. If anybody else has them, please feel free to throw more out there. More terms. SDR, standard dynamic range. Standard dynamic range is between 1 and 300 nit. Now, what is a nit? By definition, it is the candela per square meter. Reality is, it's a unit of luminance. More of a layman's way of describing it, nit is just how bright the screen is. You know, if you look at a standard def production on a standard def, or an SDR production on an SDR monitor, you look at it and it just looks like any television you've ever had. Just, it's there. But if you look at an HDR production that's around 2,000 or 4,000 or 6,000 nits, you know it. Like a 6,000 or 4,000 or 6,000 nit screen, which is usually only done by laser projectors, they're almost like burning your retina bright. You know, 1,000 or 2,000 nit televisions is pretty normal now for what you can buy at your house. But once you get around 4, 5, 6,000 nit of brightness, it's incredibly exotic and incredibly expensive. Again, digital cinema is doing it by very literally using laser projectors. They can't even do it with LED bulbs. They have to use lasers as a light source. But the HDR standard itself, at least the way that we've implemented it, is we can go up to 10,000 nits, which is like eye-meltingly bright. You're going to be, you know, if you close your eyes after looking at that monitor, you're still going to see it for a while. It's incredibly bright. It's honestly 4,000 nit is kind of the same, it has the same effect. But HDR can go extremely bright. The standard allows for it. Again, the standard allows for stuff that the monitors can't even do. Remember back on Rec 2020, how the monitors can't even do full Rec 2020 yet? It's the same with HDR. To my knowledge, nothing that I've seen can do 10,000 nit. Again, there may be some exotic thing out there. That is a good question. What is a safe max nit for viewing? You know, I would have to say it's a relative answer, because if you're 4 inches from the monitor, probably not safe at 4,000 nits. You're gonna feel it. But you do have the law of inverse squares, so that every time that you double your space of a distance from a source emitter, that the amount of radiation received goes down by a factor of 4. So every time you double your distance from the monitor, it gets significantly less harsh on your eyeballs. So take that with a grain of salt, but it is just another part of HDR that is wildly relative. But good question, though, and also kind of a fun one. So how do we get from SDR today to HDR? How do we get it to the home? How do we broadcast it? How do we get that extra contrast, that extra brightness? Well, you all may have heard of a thing called HLG, hyperlog gamma. The BBC and a few other people were very involved in this. And HLG is kind of brilliant in a few ways. And this is what a lot of our productions have been done over the past, well, many years. If you go to almost any live production whether it's a production truck or whether it's a studio, almost all of them are done in HLG today. And it's interesting what that reason is. HLG will still work on an SDR television. So if you do an entire production in HLG and you send that signal to a standard television that might not be HDR, it'll still look more or less fine. And that's the reason we've adopted it. HLG just makes everything brighter. It just adds, that data range that we had on an SDR from 1 to 300 nit. HLG, the industry is more or less coalesced around 1000 nit is the goal for HLG for brightness. And that's what HLG does. It just makes it brighter. It's that simple. And that's why we've adopted it, because if you are in a production truck, you don't have to buy all new monitors or all new multiviewers to do HLG productions. You can just do it. Let's see. It looks like we do have a question. No questions are dumb because that's how you learn. Now we have new compression methods like H.266. How does stream compression affect the HDR? We'll talk about that a little bit here in the end. Because the compression technologies are getting better and the amount of bandwidth they require is getting less and less, although they're incredibly more computationally intensive. So we'll dive into that a little bit as we go through the presentation, but I'm glad you brought it up. And is it correct to say that HLG is the HDR standards in sports production nowadays? Largely, yes. You are absolutely correct in that, but it's changing to the other standard, and we're about to address why. Because again, HLG is has the advantage that the monitors in your production control rooms today will work. The multiviewers in your production control rooms today will work. And that HLG signal sent to an SDR television will still look fine. That's the advantage of HLG. And what does HLG do? It just makes the video brighter. So you get brighter video. You get to use the televisions your customers currently have. You get to use the infrastructure that your broadcaster currently has. Sounds like a win, right? That's why everybody's adopted HLG. But again, let's go back to the human eye. And if you all would love to have some light reading, depends on your perspective on mathematics, something that'll absolutely put you to sleep. Peter Barton did a fantastic paper on how the human eye can see and perceive contrast, and how the human eye can perceive changes in contrast based on how bright the video is. Again, it's a fantastic read. The next 5 to 10 minutes of our discussion is based on this paper. Light reading. You know what? I wish I could actually take credit for doing that. Thank you for catching that. I wish I would have done that intentionally. But let's read a slide right now for everybody who might be diving into this a little bit, maybe on a mobile device. The Barton threshold refers to a model of human visual perception developed by Peter Barton. It describes a relationship between luminance, spatial frequency, and the ability of the human eye to distinguish between different levels of contrast. Essentially, it establishes a threshold below which the human visual system cannot reliably perceive contrast differences, meaning an image or pattern becomes indistinguishable from its background. Well, what does this tell us as an engineer? As an engineer, I see this as anything that is outside of the Barton threshold. My human eye can't perceive the changes anyway, so why would I broadcast that data? Did I maybe just find a way of compressing the video in a way that the human eyeball won't be able to detect anyway? So Barton created what's called the Barton ramp. As you can see on the right here, we'll take it a little bit more full screen. And what you've seen is as the human eyeball is actually incredibly sensitive at detecting differences in contrast in very low light, in the blacks and in the grays of an image. Now, again, let's think about this for human evolution. Wouldn't it be great if at 2 o'clock in the morning you're doing whatever you're doing outside of the house at 2 o'clock in the morning and you see a tree rustle and you have a panther trying to eat you? Granted, we've gone back about 100,000 years in human evolution, but if you are able to see it and live, you get to pass your genes on to other people. Therefore, humans have developed the ability to see things relatively with a very large amount of sensitivity in the dark. What does that mean for television? That means that the human eyeball can really perceive subtleties in dark video, whether it's dark grays or in the blacks or things along those lines. So if the human eyeball is able to very much perceive things in the gray and the black region, wouldn't it be worth it for us to broadcast video with extra bandwidth in the grays and the blacks, and maybe not so much in the very brights? Because remember, the human eyeball can see brights, but it doesn't see the level of detail in contrast in the very bright light as it does in the very dark parts of the video. So there is a standard called PQ, and I'll give Dolby credit where Dolby gets credit for. They kind of pushed this through as a standard, and they also left it open so people can adopt it. But there is a thing called PQ. It's perceptual quantization. And it is the highest quality video that you can fit in terms of contrast ratios and so forth within a 10-bit bandwidth. And remember, everything in broadcast is built around 8-bit for older stuff, but for the most part, everything in broadcast for a very long time now has been 10-bit. So that's our functional limitation. Well, Robert, you just said that there's this way of transmitting video that emulates what the human eyeball can do. Why don't we do that? Why do we do HLG? Well, to be honest, PQ does not work in SDR monitors. If you send a SDR or a PQ signal to an SDR monitor, it's not like the monitor is going to burst into flames. It just looks awful. I mean, that's the reality of it. And I hate to say it, but this is why that the broadcast has not adopted PQ in a very large amount until very recently, is to do a production in PQ. You have to, it looks like somebody's cat walked over a keyboard. It looks like you have to replace your monitors. You have to replace your multi-viewers. You have to replace a lot of your infrastructure. Almost all of your encoders have to be done to be able to support PQ. And that's a very critical step. We're starting to see people do productions now natively in PQ, and that's something that we're focusing on. But you'll notice from the slide, PQ emulates that Barton threshold. So now granted, the 10-bit is just right above the Barton threshold, which means that we could potentially see some artifacting. Not much, but we could potentially see a little bit at 10-bit. But it's as good as we can get for a 10-bit infrastructure. Now, there is some infrastructures now that support 12-bit. And the advantage to 12-bit is, you notice we're on the other side of the Barton threshold, which means anything done in 12-bit is going to be better than what the human eyeball can perceive, which means it's going to be the highest quality signal we can possibly do ever for the human to see. It's pretty fantastic. So remember, 10-bit just above the Barton threshold, 12-bit just below the Barton threshold. But the most important part is PQ, using all of the work that Barton did, is the highest quality video in terms of luminance and in terms of contrast ratios that we can send to the home, because the eyeball is sensitive around grays and blacks, and PQ knows that and is designed around it. Also, PQ in the distribution domain is the basis of Dolby Vision, HDR10, and HDR10+, which is a very good time to talk about a couple questions that have come in. So first off, but wait, there's more. HDR10, Dolby Vision, HDR10+. Why are so many broadcasters using HDR10 Variance. Well, it's actually very interesting. HDR10, again, is PQ is the basics of Dolby Vision, HDR10, HDR10 Plus. What are the differences? Well, Dolby Vision, I think I have to pay Dolby 50 cents or something just from saying that word, um, is based on PQ, but Dolby Vision has the ability to change its look and its how the monitor displays the signal based on the metadata that's in line. What's really interesting, and this also works for HDR10 Plus, is monitors have different capabilities. Some are brighter, some are dimmer. Some are a little better in blue and a little worse in red. Some are fantastic in green and awful in blue and so forth. All monitors have different parameter values. The metadata that's included with Dolby Vision and also the metadata that's included with HDR10 Plus has been designed so that the creative intent, the intent of the content creator is mapped correctly in luminance and chrominance values once it hits the monitor at home. So you're not just sending the PQ signal, you're also sending metadata along with that signal to allow the monitor to, it's called an electrical EOTF, electrical to optical transform function. It is a transform function that's sent along with that metadata that allows the video to look as close as it can to the original creator's intent. So Dolby Vision is Dolby's way of doing it. HDR10 Plus is how a lot of other vendors have done the same thing. They just don't have to pay Dolby to do it. So you want to know why there's two different standards between Dolby Vision and HDR10 Plus? It actually has to do primarily with royalties. The fundamental technology is fairly similar. HDR10 Plus is actually just PQ with no metadata. I mean, there can be metadata on it, but it's not going to change scenes based off the metadata. So HDR10 is a very simple way of getting the data out there. Another question, slightly off topic. Does Tag MCM have the ability to detect if a video source is HLG versus, say, PQ? And can it alarm on that? If the Tag system as a whole, which is a combination of MCM and MCS, can do that. Not only can we detect HLG and PQ, we can look at the metadata, we can display it, we can display the HLG and the PQ on the same monitor, we can do all of it. So short answer is yes. And what considerations should we take into account when converting from 1080p HDR to 1080i SDR in HLG? We can spend an entire hour on that. That is probably the hardest part of HDR workflows today. And I have 2 slides dedicated to it because that's what we have time for. That is a very good question of which we will spend more time for at the very end of this. But converting between HDR and SDR is, well, we spend the very end of this presentation talking about that. So I'll get back to that one. So yeah, PQ. If you want my own, this is taking my tag hat off. This is taking whatever. This is my own personal opinion. With everybody talking about 4K and 8K and HLG and PQ and all this sort of stuff, if you want my personal opinion, 1080p PQ in terms of how much bandwidth you spend and what the consumer at home can see is the unicorn. Because once you hit a lot of compression, unless it's a very big stream, you can't see a whole lot of difference between 4K and 1080p unless your TV is gigantic. Everybody can see a difference between an SDR and HDR. And as we'll see from this next slide, you will notice, by the way, right here, this red line going straight through, that's HLG. So you notice HLG here doesn't spend hardly any of its bandwidth focusing on the grays and the blacks, what the human can really see. HLG just makes it brighter. That's it. So, the 1080p PQ, in my opinion, is as a function of bandwidth the best signal you can get to the home, because you can see the spatial resolution fantastically in 1080p 60 or 50 for everybody else in the rest of the world. I'm not trying to be too North America centric here. And PQ is the closest to emulating the signal as what the human eyeball can see. And so this is actually an interesting chart for me, at least, by the way, because you see the Barton ramp here, the purple dash line, So that's essentially what the human eyeball can perceive. And then here we have this gray line, which is your 10-bit PQ set at 1K, 1000 nit brightness. By the way, it is worth pointing out, just because it's on the screen, that PQ and Dolby Vision actually do allow for 10,000 nit. The standard's there, but you can't fit it in 10-bit. So you're probably not going to see that too much in live real-time productions anytime soon until we make a jump to 12 or 16-bit. But it does allow for it. It is there. And this is the last part, the point I really want to point out is the red line here is HLG. Notice HLG does make it brighter, but this part is on the other side of the ramp. So the human eyeball really can't perceive that extra brightness that well. And then it doesn't send a whole lot of data around in the grays and the blacks where it really matters. Again, HLG just kind of makes it brighter. And one part I do want to add to this because it's fun, and I've been talking about how subjective HDR is. So this has all been primarily based off of the Barton ramp or the Barton threshold. There is another paper out there called the Schreiber threshold that actually their interpretation of how the human eyeball is able to perceive contrast and light values is different than the Barton ramp. So I wanted to make sure that was still in this slide, so you can see how subjective HDR is, how subjective how we perceive contrast and how we perceive light is. Question that just came in said, so SDR would be the red line stopping at 300 nits. That is correct. Anything here that's around 300 nit, that's going to be your end threshold for SDR. You're absolutely correct in that. And that also, again, depends on the monitor. Some monitors are only able to do 100 nit or 200 nit. Most LCDs can now do 300 nowadays. So again, this is where things are kind of wildly subjective based off of the monitor. And that the difference in monitors and how monitors do color mapping and tone mapping and contrast mapping, that's why Dolby Vision exists. That's why HDR 10 plus exists. So they can send metadata along with that signal to be able to adapt for the capabilities of that monitor. Thank you for the question, and you're absolutely right. So let's have a little bit of talk about 8-bit, 10-bit, or 12-bit. If 10-bit is the most optimized version of the content, does it make sense to master in 12-bit if you can? Or Ari asked a question earlier about pulling higher quality off the imager. Why not pull a 14-bit or 16-bit off the sensor and just sleep much easier? Because if you do a 16-bit 444 capture off of an imager, it's very easy to go to HLG or PQ because you're taking a lot of data and you're stripping that data out to be able to map it into a 10-bit workflow or into a 12-bit workflow or to be able to map it into an HLG curve or into a P curve. It's way easier and always better to have more data than you need to pull it down into a 10-bit or 12-bit workflow. Now, 12-bit gives you a graceful conversion to HLG and PQ and 10-bit, but a lot of broadcast infrastructure doesn't support it yet. It's also quite a bit more bandwidth, 20% more bandwidth. So, it's weird to say this now, but 3 gigabit per second in a 2110 environment for a 1080p 60 signal was a huge deal a couple years ago. And I hate to say that's not that big of a deal now, but now that 400 gig switches are shipping and we got 800 on the horizon, we're getting to the point now, well, why don't we just do things in 12-bit? Or why don't we just do things in 16-bit? Because the infrastructure could potentially allow for it. It's something to consider, but definitely for post-production environments, if you can pull raw 16-bit off the imager, do it. And then later master that down to 10-bit for your productions. But if you're doing a live production, you're going to be 10-bit today. There's a few 12-bits floating around, but for the most part, you're going to be 10-bit. But this is a good point of if you're doing a production and you have the capability of capturing more bit depth than you need, do it. If you don't, you don't. And that's the reality of our industry today. So going back to the question about 1080p HDR and 1080i SDR conversion, we're going to spend the last couple of minutes on this. We just have two or three slides on it. And I jokingly like to say SDR to HDR to SDR conversion, because even if you're doing a production today in HDR native, there's probably a pretty good chance that you're going to be pulling some old footage that is SDR, right? Or if you're doing an HDR production today, it is a reality that you also have to create a secondary SDR production because most distribution chains that aren't streaming, whether it's satellite, you know, dish direct, that type of thing, or terrestrial ATSC1 type things, those are still SDR today. Now, granted, dish and direct and so forth, they do have HDR channels. Some of the satellite providers in the Middle East and Europe and Asia also have 10-bit HDR channels, but that's not all of them. So we still have to do that. So any production we do today is going to be bouncing between SDR and HDR, and then probably back to SDR at some point too. And meaning this as lighthearted as I can, but also this is the seriousness of it. We all should have paid more attention in math class because anytime you convert, and I like to use this drawing here on the right between Rec 709 and Rec 2020. Say I have a video that's recorded in Rec 2020, and at the very tip over here in the green, I've got an extremely bright, extremely green color. But I need to put this Rec 2020 HDR signal into a Rec 709 SDR signal flow. How do I decide to map this extremely bright, extremely green signal into a slightly less bright, slightly less green domain? Or maybe it's one of these colors that falls in the middle here. You know, maybe in Rec 2020, some of these blues don't exist in Rec 709. So how do you convert those things? So that's kind of hard to tell. So and hard to do. So you have to do what's called a lookup table. Hold on just 2 seconds. My apologies for that. We had a little maintenance issue here. Okay, so we have lookup tables that are able to do that conversion from taking your Rec 2020 down into your Rec 709 color space. Now, how do you decide which green gets mapped into which green area? How do you decide what reds get done from that? This is the interesting part. So that's why when you do LUTs, you start to see a 2D and a 3D LUT. A 2D is a single color, a single perimeter. I want to make my greens brighter. I want to make my blues brighter. I want to make my reds brighter or more dimmer or whatnot. And then the 3D color space is the interesting one. And the 3D color space is how do I map all the reds, all the blues, all the greens, and all the associated luminance values into a Rec 2020 down to a Rec 709 or so forth. Interesting how that all kind of plays out. So this is very highly subjective. I like to use an example of a college football team that has red in their logo. If you shoot a HDR production and they have that very unique red in their logo on their field, it's on their jerseys, it's on their signs, it's on all that. And that needs to be converted to SDR. You want that red to look accurate, right? Now, a standard LUT may not be able to do that accurately. The standard LUT may have to have some conversion. A standard LUT may have to make that red look as it's not intended. So this is where things are highly subjective. You want to protect that red. So you're going to create a LUT that converts from SDR to HDR or HDR from SDR to make sure that red is protected. NBC and BBC have actually done a lot of work for all of us. They have created their own LUTs. to go from SDR to HDR and HDR to SDR, and also to the question about 1080p HDR and HLG down to a 1080i SDR. That's all done. That's all how it is with their LUT. So if you use their LUT, you are essentially going to get a pretty good quality signal. What's fantastic, and I do highly recommend you all doing some reading on this, is look at the NBC and look at the BBC's websites for these. The NBC LUT has a GitHub. You can look at all of their LUTs from HLG to SDR, SDR to HLG, PQ to SDR, all the different conversions you may want to do for the LUTs. It's all there, including all of the LUT files, which are actually pretty incredible to see. BBC has an entire website dedicated to their LUT and a lot of the reasoning and rationale behind it. So if you want to understand why they did what they did, both NBC and BBC have done a very good job of explaining those LUTs. So I can definitely say for most productions today that HDR to SDR and SDR to HDR conversions in those LUTs is 99% of the problems we have in HDR productions today. Anytime you convert from Rec 2020 to Rec 709, from HLG to SDR, from PQ to HLG, anytime you convert from one color space to the next, from one chroma or from luminance map to another luminance map, you will have to do a LUT. And those LUTs are always highly subjective. That's where you're going to spend your time. That's where a lot of the troubles lie. And that's also where your test and monitoring systems need to be in good shape. Because if you have a signal that is in HDR and you try to send it to an SDR destination, you're going to want an alarm on that. Or if you have an SDR source and you're trying to put it into an HDR production, you're probably going to want to know that before you try to do it, right? So having a monitoring, probing, and analyzing system that can identify sources that are SDR and HDR or HLG or PQ is absolutely critical for that. But the biggest thing I do have to say is understand the LUTs, understand the conversion technology, because 90% of what you're going to do today is going to be a problem with that. Let's see, we have a question that just came in. You mentioned HLG and HDR10. What are your thoughts on Technicolor? Seems to have the right capabilities in terms of backwards compatibility for SDR and also support for dynamic metadata. You are right. So Technicolor does have their own standard. And from what I've seen of it, I do like it. I am a fan of it. It is a newer ish technology in the domain. It doesn't quite have the adaptation for live production as HLG or PQ does. But for the distribution domain, I think it's fantastic and something that everybody has to take a really good look at. Another question that came in, why when you shoot on a set monitor, especially with reds, they never match? If the TVs look correct, the camera feeds look off. I often have to adjust an onset screen to look good in the shadowing station. You're right. And this is the difference of television monitors. Also, cameras have their own sensitivities. Depends on what camera manufacturer you use. Going from a Grass Valley camera to a Sony to a Red or whatnot, imagers and their processors. Because remember, you're doing a conversion from 16-bit to 10 or 16-bit to 12 or whatever. They're doing conversions. So the monitors have their own conversions. The cameras have their own conversions. So you're talking about one of the harder parts of these productions. And you're absolutely right on that is one of the troublesome parts of it. Let's see, another question. HLG doesn't have metadata, but it should have flags in the SDI signal to indicate it as HLG, correct? You are correct. You can set flags in SDI. You can also set flags definitely in 2110 that can alert the downstream devices that this is a HLG or a HDR signal. That's all there 100%. And we highly recommend using those flags as they are. Once you get into the IP domain, especially in compressed, especially and even 2110 supports this, there's a lot more flags for dynamic metadata, a lot more flags for what the NIT values are, color space, all that sort of stuff. SDI has a little bit more limitations around it, but all that dynamic metadata is in there. All right. Okay, loaded question. This will be the last one for the sake of time. A loaded question, but are there standards for HLG color space LUT metadata tags? Yes, there are, but there's different standards for how the technology goes around. For example, in 2110, you have the SDP files that are able to hold a lot of that data. But if you go to at-home distribution, that metadata is done via a mechanism with inside Dolby Vision or a mechanism that's with inside uh, HDR 10 plus. So it kind of depends on where your workflow is you have different standards for that. So we are right at the time. I wanted to thank everybody so much for the questions and for your participation here. It's wonderful, and I very much appreciate it. And if you have any more questions, if I didn't answer anything quite enough, or if you need more detail, I'm here to help. I'm here to be a resource. The rest of TAG is here to help. A lot of what I know, I have learned from the people here at TAG. TAG also will have a white paper that addresses a lot of these standards and so forth. So please feel free to look at those white papers. Feel free to email, call, text, ask us at any time. We're here to be a resource. Thank you very much and have a fantastic